affecting rates and graphing. You will see the graphing really come into play on the Kinetics 1 and the Kinetics 2 lab. I will upload a graphing module that shows you how to graph different reactions as we go forward, because in lab, pretty much from this point on, you will have to submit a graph for almost all the labs. And not only do you have to submit the graph, but you need the data off of it. So when the graphing module goes up, make sure that you reference it when you need it. All right, factors that affect reaction rate. Now, this is actually pretty simple and pretty straightforward, and some of it's really common sense. But a lot of times you have to think about things. So the first thing is we're going to talk about the nature of the reactants. Well, what you find out is that ionic compounds react very quickly. And you saw this when we did titrations in 1211. You're going to do titrations in 1212. You add a drop, it swirls, it's done. It's instantaneous to all effects and purposes. That's an ionic compound. Molecular compounds, on the other hand, are slow. They are slow because in order for a molecular compound to react, you have to break bonds, then you have to rearrange, then you have to reform the bonds. So it takes a lot of energy and a lot of time. Think about throwing magnets together and they just go suck together. No problem. That's an ionic. Okay, think about unsnapping items together. Kids' toys do this, and then you have to snap them back together in different amounts. That it takes a whole lot more time. Now, and remember, molecular compounds have covalent bonds. Now, if that's not bad enough, strong covalent bonds are even worse. These are very slow. And again, we're back into organic, and this is not an organic class, but you're used to the titration instant gratification. Well, in organic, you may have to run the reaction for an hour to get a good yield. And that's the lab reactions. If we're not working in labs like in the drug companies and they're making a drug and it's real complicated, it may take a week, a month to run a batch. And the yields tend to be low too, but that's a different story. And the reason why is because it takes so much energy. Quick question. What is the major component of air? Yeah, it's not oxygen. It is nitrogen. Nitrogen is the main component of air. Why? And here's the other thing. Nitrogen is critical for plants to grow. What is the main source of getting nitrogen from the atmosphere to the ground? Trivia for the day. Lightning strikes. Why? Because nitrogen has a triple bond. So not only is it a covalent bond and you have to break it up, but it's a really strong covalent bond. Does that want to break up? No. That is why nitrogen is the major component in air, because it does not play well with others. Basically, it takes too much energy to break it up. Okay? So that's the first rule, nature of the reactants. Are they ionic? Are they covalent? Are they strong covalent? Etc. The second thing is the concentration and state of subdivision, which are kind of the same, kind of different. Okay, as you increase the concentration, you're going to increase the rate of the reaction. We'll get to the actual model for a reaction later, but basically, in order for things to react, they have to come together, collide, right? So as you increase the concentration, you increase the rate. Well, actually, this is kind of pertinent. We've been in the middle of the COVID, especially in the spring. Nobody went out. Okay, so if you drove anywhere, and yes, I did, doctor's appointments, etc. I was good. If you drove anywhere It was really freaky because there was nobody else on the road. So during the COVID pandemic, those couple months, a lot of the insurance companies gave back money. Why? Because they didn't have any crashes on the road because nobody was on the road. So therefore, a number of the big ones gave back part of your premium because you weren't driving. So therefore, you got your money back. Now, if you did some driving, you just lucked out. But there's your concentration. You increase the concentration, you increase the rate, chance of a collision. Same thing with cars. Now, the other thing is that when you're talking about a reaction, most reactions, if you're encountering a surface, will only react at the surface. So you can have a chunk of iron, cast iron pan. It is not going to react. Why? Because you can only access the iron atoms on the surface, which really aren't that many. But if you start breaking it up, then you're going to increase the surface area. And as you increase the surface area, you increase the rate. And I'll show you a cool slide next one that shows this. Again, you're back to if you're going to build a fire, you're out camping, you don't start with a 6-inch log. You can't get a fire built with that. You run around, find twigs, leaves, little things. They may have the exact same wood content, and sawdust is fabulous for this. Same content as the wood you got it from, but the wood you got it from you can't start a fire with, but you can start a fire with the shavings because the surface area is higher. The other two factors, which we will go into much more detail later, so I'm just going to list them here, are temperature and the presence of a catalyst. Now, a catalyst is interesting because it is not consumed in the reaction. Again, much more details about that later as we go. But right now, there are 4 factors that affect reaction rates. Now, be careful because these are covered kind of in the book, different places, but I put them all together because this becomes critical in thinking about whether a compound or reaction is going to take place quickly, slowly. Some things you have no control over, other things you do. Here's one of my favorites. Fire is fun to play with. Be safe. Is steel wool. Steel wool is iron. It is the exact same thing that is made up of cast iron pots. But cast iron pots don't burn. Steel wool does, and it actually burns very well and very hot. And it's because the surface area is so tremendously large that it'll react faster. Same thing if you think about it as magnesium strips. If you're, again, camping, if you're not a camper, then let it go. But when you're camping, they have a big chunk of magnesium you can buy that you scrape off, and it lights readily once you scrape it off. But you can carry around that magnesium chunk in your pocket, big fat deal. But the minute you make it much smaller, it becomes much more flammable. Okay? So that brings us to a summary table. There's one similar in your text. This one was from the previous edition of a Pearson text. I like it because it puts it all together. We have a 0 order, a first order, and a second order rate. You tend to not have higher, except on paper. So you'll have your rate law associated with it, the units of K. This is your integrated rate law. More about that as we go through it. Now, here's where we get, and we'll do the half-life in, I think, the next section. But this is where this applies to lab. And you'll do this in the kinetics 1 equation. Is you're going to graph time versus concentration, time versus the natural log of concentration, and time versus 1 over A. Now, all of them give you linear plots. The first two, first and 0 and first order, are negative, and second order is positive. And how good the line is based upon your R squared value. That tells you your best fit, or your fit. I shouldn't say best fit. It tells you your fit, and your maximum is 1. So if you're graphing some data and you get a R squared value for the line closer to 1 for this graph, then that would be 0 order. If it's closer to the natural log one, it's first order. And if it's second order, it's the graph of 1 time versus 1 over concentration. More about that again in lab. I'll go through that in detail in the graphing. But the beauty of this chart is it kind of puts all things together and labeled. You will have these equations, not the graphs, on the formula sheet. You'll actually have all of them. They may not be labeled. I try to keep them in order in terms of I do 0 order, first order, and second order, and do all the variations together. However, I don't label them per se. Now, this is another graph. This again is time versus concentration. If you get the slope here, you know that this is a 0 order reaction. If you're just looking at the concentration drop, that's all this is here, you'll see a curve. If it's 0 order, you get the line here, first order, etc. If you're graphing it with the rate versus the concentration, then 0 order flat lines. That means it's either on or off. First order is linear and second order has a curve. I prefer this group here. It's easier to see, and you'll see that in the lab. Oh, here it is again. This is the axes in lab. Notice it's what you're graphing it against as to whether it's 0 first or second order. And again, you'll be needing that in the Kinetics 1 lab, and the graphing will go up. And the graphing demo actually will be for a variety of graphing, freezing point, Kinetics 1, Kinetics 2, etc. I'll do several so you can go back and view it. I will post a demo of what the graph should look like in the end for those of you who are not Excel challenged. If you are Excel challenged or you never graphed anything, which is actually not that uncommon, watch the demo. And if you still have questions, contact me on via email. Send me an email and a couple times, and we'll set up a review session. Review sessions will, like office hours, will be starting this week. But remember, you can always send me a question and we can do a review session. Or even if you can't do the review session, you can send me a question and I can try to email you back.